Welcome back to another lesson on sequences. Today we're going to be taking a look at a mix of arithmetic, geometric, and neither sequences. Let's take a look at number 5 here. 2, 9, 20, 35, and 54. As we said before, if you want to find if it's arithmetic, you should be adding the same number every time. That is definitely not the case. How about multiplying? Can we multiply by the same number every time? That doesn't look like it's the case either. So therefore, this is going to be a neither sequence. For that reason, when we create neither sequences, we show our work by building a table. We can have our term number for the x values and the value for the y values. We have 5 terms, 1, 2, 3, 4, and 5. And then we have term values 2, 9, 20, 35, and 54. Okay. All right. So from there, let's see what's happening here. Looks like from 2 to 9, we are adding 7, and then 9 to 20, we are adding 11. Here we're adding 15, and here we're adding 19. All right. Well, what's going on here? Well, this is actually pretty nice. It looks like we have a common difference of 4 among each of these if we were to apply that the second time around. Remember what we said in our Zoom session last week, which was if you have this occur that second time around, then this is leading you to see that you've got some kind of quadratic in the mix. So we know we have some kind of like n squared in some way. Maybe it's like n squared plus 2n plus 3 or something along those lines. We just know it's some kind of quadratic. Okay, so because it's a quadratic, you basically know it's in its most basic form, it's something times something. So let's go ahead and set up our problems here. We know that 2 is going to be something times something. 9 is something times something. 20 something times something. 35 something times something. And 54 something times something. Just like we said in our Zoom lesson last week, it's really just a guess and check, just playing around with it and seeing what works. So if I just play around with numbers, this whatever I write down right now, it may or may not work. I don't know, but I'm just trying things out, so let's just see what happens. I think 20 is 5 times 4. You could have also said 10 times 2. Oh, look at this. This is interesting. But I'm also saying that I want to try to develop some kind of pattern as the numbers are going from term number to term number, right? 1, 2, 3. It's going in order. I'm going down 1, 2, 3. Here I'm going down. Look at this. This is interesting. 2, 3, 4. And so, as I start to see a pattern emerge, I may want to try to work a little bit more closely at what those numbers would be. If I have 35, I want this to be a 5. Maybe this will be the 7 then, right? 7 times 5. 54, 9 times 6. Looks like that actually works pretty nicely, doesn't it? So it looks like we got it in our first shot. That was pretty nice. What we see here is that as we go down 2, 3, 4, 5, 6, well, that's going down from term 1. If I'm at term 1, notice how term 1 associated with with the value 2. 1, it gives me 2. 2 gives me 3. 3 gives me 4. 4 gives me 5. 5 gives me 6. Or in other words, whatever term I have, I'm basically taking that and adding 1 to it every time. That's how I'm getting the second term here. And then I multiply that by, well, how am I getting those first numbers? 1, 3, 5, 7, 9. What are those? Well, those are all odd numbers. How do you get odd numbers? Well, you take an even number and you either add or subtract 1, right? That gives you an odd number. Okay, so if I want an even number, I want to try to come up with some kind of even number. So maybe like 2n. Let's see, if I multiply 2 times my term value of 1, that'll give me 2. But then I want that to give me a value of 1. So 2 times 1 will give me 2. To get 1, maybe I have to subtract 1, huh? 2 times 2 is 4. Minus 1, yeah, that's 3. 2 times 3 is 6. Minus 1, yep, that's 5. Okay, so it looks like this is going to be our pattern here. 2n minus 1 times n plus 1. Remember, it's all just a guessing game. Just guess and check, trial and error. If it doesn't work, try another pattern out. Okay, but here it looks like we were able to get our sequence. So that's pretty nice. All right. Remember, because this is on a video, feel free to pause if you need to, rewind it, rewatch it if you need to. My recommendation is you try this on your own just to get into the hang of it and see if it works out for you. Okay? But that's probably not what you're going to do, huh? You're probably just going to copy what you see on the video. That's it. All right, well, let's just go on to number 6, okay? So let's take a look at 0, 2, 5, 9, and 14. Let's go ahead and we see right away that is not arithmetic. It is not geometric either. So this is going to be another neither sequence. So for that reason, we build our table, term number versus the value. We have what? 5 terms? 1, 2, 3, 4, 5 terms. We have 0, 2, 5, 9, and 14 there. All right, let's go at it. So we see here, we knew it was not arithmetic. We have to add 2, but then we add 3. Looks like we're adding 4 again. Okay, look at that. See, it's not arithmetic. But what we do see is that common difference occurs the second time around. When that occurs, you know you're dealing with a quadratic. So for that reason, we can just go ahead and set this up to say something times something gives us these values. Oops, let's keep this all lined up so it's easier to see the pattern. Okay? Like that. All right, so, well, 0 is pretty easy, right? We know that anything times 0 gives us 0, so 0 times anything, right there. I don't know what that other number is, though, so I'm going to leave that blank for now. What gives 2? Let's say I want to see somehow a pattern emerge. Maybe I can go 0, then 1, so 1 times 2 would give us that, right? Maybe that wouldn't work. I don't know. Maybe it's actually 0 times 2. Maybe what I want to think of is how everything can maybe go in terms of 2s. Maybe something like this. I don't know what's going to work right now. I'm just going to go ahead and just see what happens the first time around when I did that 1 first. So let's try that first. So 0, 1, maybe this might be 2, huh? 2, 3, 4. Let's see. 9 is 3 times 3. 5. That's 5 over 2 times 2. Maybe that might work. And then what? 14 is 14 over 4, maybe? That'll give us 14, right? The 4's cancel out. Let's see, does that work out? This is the same as 7 over 2. 3 is 6 over 2. Here's 5 over 2. Here's 4 over 2. Look, our pattern's emerging. This must be 0 times 3 over 2, right? All right, looks like we got our pattern. Well, we got 0, 1, 2, 3, 4. How do we get that from the term numbers? Notice how it's always the term number, and then it's basically minus 1, right? So we're going to take the term number n, and then subtract 1 from it. That'll give us our first column right here that you see there. Okay. Times, let's see what we got over here. Notice how everything always has over 2, over 2, over 2. I'm going to put this as over 2. And then just take a look at that pattern that you see there, going from 3 to 4, 4 to 5, 5 to 6, 6 to 7. How do we get that from term number? 1 gives us 3, 2 gives us 4, 3 gives us 5, 4 gives us 6, right? You're basically taking the term number and looks like we're adding 2, huh? So we have n minus 1 times n plus 2 all over 2, like that. That'll be your sequence, okay? Now, interesting thing about this problem is there's actually another way you can look at this. I'm going to go ahead and put this as method 2, okay? In method 2, notice the sequence that we have again. I'm going to say term number versus value. And then we have 1, 2, 3, 4, 5 again. And then we have 0, 2, 5, 9, and 14. The cool thing about this is actually this sequence looks pretty familiar. Imagine I were to take the sequence and add 1 to every value. Go ahead and add 1. What do you get? You get 1, 3, 6, 10, 15. Hopefully, in your head, you're thinking, I've seen that before, right? 1, 3, 6, 10, 15. Where have you seen that? Well, that was last week in our Zoom session. We did 1, 3, 6, 10, 15. It's the exact same pattern. We had that n times n plus 1 all over 2, right? So we can go ahead and use that. This sequence is basically n times n plus 1 all over 2. That's how we get 1, 3, 6, 10, 15. But that's not really the sequence we want this time. We wanted to backtrack. We wanted 1 to be 0, 3 to be 2, 6 to be 5, right? And what are we doing there? We're just taking our original sequence, this one, and then subtracting 1. There you go. That's another way you can write the sequence. And just to double check your work, what you could do is just multiply it out, see what you get. In this first case, or rather in method 2, what we see is this is going to become n squared plus n all over 2. And getting common denominators, I would have to subtract 2. So basically this is like minus 2 all over 2, like that, right? So this is what we get if we were to simplify everything. Well, what happens when we simplify this case? Let's see. FOIL this. N times n is n squared. N times 2n is 2n. Negative 1 times n is minus n. So 2n minus n gives us n. And then minus 2. All over, common denominator of 2. Look at that. Same exact formula. Okay, so this shows us that there are two ways of approaching this. You can take what you already know and just apply some trivial arithmetic to it, or you can go with the pattern route too. Okay. All right, let's go on to some more. Number 13. Is that the one we're on? Number 13? Nope, not number 13. Let's go with more. 7, number 7. All right, so we got 2, 6, 12, 20, and 30. So just like we've done before, hopefully you're seeing, this is not arithmetic. Is that geometric times 3? Nope, it's not geometric either, okay? So because of that, we can go ahead and make our table. We have 5 terms. And then we write our numbers down, 2, 6, 12, 20, and 30. Add 4, add 6, add 8, add 10. Add 2, add 2, add 2. Well, if that's the case, we know this is going to be a quadratic again, something times something. So what times what gives us 2, 6, 12, 20, and 30. Let's give it a try. Play around with numbers. 2, 1 times 2, 6, 2 times 3. Ooh, look at this. 1, 2, try to go with that pattern. 2, 3, try to go with that pattern. So 12, I do have 6 times 2, but if I want to stick with this pattern, it looks like I'd have to have 3 and 4, right? 3 times 4. 3 times 4 gives us 12. 4 and 5 give us 20. 5 and 6 give us 30. Look at that. Oh, that's beautiful. That looks great. All right, so with that pattern that we see here, look at this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Well, that just looks like it is n times 2, 3, 4, 5, 6. How do you get that from 1, 2, 3, 4, 5? Just take the n value and add 1. There you go. Okay. Or another cool trick, method 2. You have 2, 6, 12, 20, 30. Look at that. Those are all even numbers, right? Let's try dividing everything by 2. Or maybe not dividing everything by 2, but factoring 2 out. 2 times 1. 2 times 3. 2 times 6. 2 times 10. 2 times 15. And hopefully what you see is 1, 3, 6, 10, 15. Look at that. The same pattern we saw before, which was, technically, this is the same as n times n plus 1 all over 2. What do we do with that sequence? We multiply everything by 2. Well, notice here, 2 times over 2 cancel out. And look at that. We're left with n times n plus 1, just like we saw in the previous step. Same answer. Okay, so different ways of approaching number 7 here. All right, number 8. 1, 2, 3, 4, 5. I definitely see this is not going to be arithmetic. It's not geometric either, so I'm just going to build my table. There we go. Okay. All right. Add 2. Add 3. Add 4. Add 5. Add 1. Add 1. Add 1. Oops, add 1. Okay, so again, we know this is going to be some kind of quadratic. Something times something, right? Now, you can play around with this quite a bit. This is going to be actually a pretty frustrating problem. It turns out that this really doesn't work too well with trial and error. It's easier to see that this is being developed from an older sequence that we've seen before. Hopefully you can see that if you if you subtract 1 from everything, you're going to get 1, 3, 6, 10, and 15 again, really. So you're just going to take this value, 1, 3, 6, 10, 15, which we know to be n times n plus 1 all over 2. And how do we get 2, 4, 7, 11, 16? We add 1 to everything. So if we add 1 to everything, let's just take this and add 1. That's going to be our sequence. Okay? All right, number 9. 0, 1, 3, 7, 15. Let's give it a try. This is definitely not arithmetic. It's not geometric either. 0 times something always gives us 0 anyway. So therefore, it's going to be a neither. So let's go ahead and build our table. I'm running out of room, so I'm not labeling the x and y anymore. You don't really need to either. You can just write it like this. All right, let's see what we got here. We are adding 1. We're adding 2. We're adding 4. Interesting. Here, we're adding 8. Wow, this is different. Look at that. 1, 2, 4, 8. It's no longer consistent like what we've seen before. This is adding 1, adding 2, adding 4. Okay, so something to notice here is that you're not going to get a common difference every time. Notice what's happening is you're always going to be adding by some value like this, right? You're always adding 8 like this. So 1, 2, 4, 8, 1, 2, 4, 8. This keeps repeating 1, 2, 4, 8, and so on and so on. So this is actually not a quadratic. Okay? When you see something like this occur, this is actually creating a geometric series. A geometric series occurs when you see that 1, 2, 4, 8, 1, 2, 4, 8, that not common difference, but you're adding the same amount every time. Well, that's just kind of showing you maybe we were looking at it the wrong way. Maybe instead, I'm going to go ahead and erase this. Feel free to do this on another blank spot, but I am just running out of room here. Maybe I didn't want to add. Maybe instead what I wanted to do was just think about how, with this 1, this 2, this 4, and this 8, maybe what I want to see instead is that this is a multiplication factor of 2 times 2 times 2. That's what's telling us we have a geometric series. Okay, so this repeated common ratio of times 2 is going to be show us a geometric series. So in that regard, what we're going to do is think about this as repeated multiplication. Now that times 2, it looks like you're going to be multiplying 2 repeatedly. So just think about how when you come up with these values, think about how that repeated multiplication can occur. 2 times some power. We want to get 0. Okay, well, let's think about this. 2 to the first power, or not first power, but we want to get the value of 1. How are we going to get that value of 1? Okay, so you want to think about repeated multiplication. Now remember that you're going to multiply 2 more and more times like this as you go on. So you want to think about how you're going to get those values equal there. Okay, so how is this happening? Well, how can we get 15? If I think of repeated multiplication with 2's, then I know that 2 to the power of 4 is 16, right? So that's pretty close to 15. Maybe I just have to subtract 1. How can I get 8? Well, repeated multiplication of 2 is like 2 to the 3rd. That's 8. Pretty close to a 7. I just subtract 1 again. Look at that. A pattern's emerging again right here. How do we get 3? Well, if I repeat this pattern, I want to get pretty close to that. That would be 2 squared is 4. Maybe minus 1 is 3. Over here, how do I get 1? 2 to the first, and then that's 2, and then subtract 1, that'll give me 1. How do I get 0? 2 to the 0 is 1, minus 1. Look at that. So that pattern that emerges there, we got repeated multiplication, and then we just need to subtract 1 every time. Okay, so what's that look like in its final form? 2 to the power of, well, notice that you wanted a power of 0, even though it was term 1. You wanted a power of 1, even though it was term 2. You wanted a power of 2, even though it was term 3. You wanted a power of 3, even though it was term 4. So we're always taking 1 less than the term number. And then from that, we just have that minus 1, like that. Okay? So there's our rule. All right, let's go on to number 10. 31, 25, 19. Let's see, 1, 2. We have 3 terms, 31, 25, and 19. All right, so from 31 to 25, looks like we are subtracting 6. We're also subtracting 6. Oh, look, so we're minus 6, minus 6. What is that? Hopefully, you're saying, oh, that's an arithmetic sequence right there. Right, so because it's arithmetic, don't worry about those guessing and checking type problems. You know it's arithmetic, meaning it should be in the form of mx plus b. It's like a line. Okay, so from here, our slope is, what's our slope? -6, right? For every 1 you go down, the number decreases by 6. So our slope is -6 times the term number, -6n. And just make sure it works for each of these numbers. If I plug in 1, I'm going to get -6. How do I get 31? -6 plus 37, right? That's going to be our 0 term. You add 6 to that, you're going to get to 37. Okay, so that's our case 0. Remember, case 0 is like the b value of the y-intercept. There we go, -6n plus 37. Number 11. Let's see where we are on time. 20 minutes. All right. Number 11. 2, 10, 24, 40, and 44, and 70. Let's see what's going on here. 1, 2, 3, 4, 5 terms. And we got 2, 10, 24, 44, and 70. Remember, I'm going pretty fast because this is a recording, but feel free to pause, rewind if you need to, so that way you can copy it and make sense of what we're doing here. Okay. All right. What have we got here? Let's see. Add 8. Add 14. Add 20. And add 26. Okay. What's this? Add 6. Add 6. Add 6. Look at that. So what do we know about this? This is a quadratic. So something times something, right? All right, let's take a look. What times what gives us 2? Let's try 1 times 2 first. What times what gives us 10? Maybe 2 times 5? Let's see. What times what gives us 24? I see a pattern going here. I see 1 and 2, so maybe I want this to be a 3, huh? So 3 times 8 would give us 24. 4 times 11 would give us 44. And what's that? 5 times 14 gives us 70. Look at that. Oh, man, I'm on a roll. I get this on the first time. All right, so we got 1, 2, 3, 4, 5. Look at that. That is just like our term number. That's going to be the n value. N times 2, 5, 8, 11, 14. How do we get those numbers? Looks like we are adding 3 every time, right? We're adding 3 every time. So in a way, this alone is its own arithmetic sequence. Right here. This alone is like its own arithmetic sequence. Okay? What's that arithmetic sequence? Well, you're adding 3 every time. That is its common difference, right? So 3 times n, and you want to make sure you get this value here. So 3 times 1 will give us 3. That's the first term. So 3, but then we want 2. So minus 1 maybe? Let's see. 3 times 2, the second term, is going to give us 6. Minus 1 gives us 5. Yeah, that works. 3 times 3 is 9. Minus 1 is 8. Yeah, this works. All right, so we're going to say n times 3n minus 1. That's going to be our sequence for number 11. Okay? All right. Yeah, I guess that's all we could do with this one. Okay, let's go on to number 12. Oh, what in the world? We got a fraction here. Let's see. So we got 1, 2, 3, 4 terms. 4 terms. We have 4 thirds, 8, 48, 288. What's this? 8. Oh my gosh, that's huge. Maybe we're multiplying, huh? Maybe it's times 6. 40 times 6, 48, 4, 24. Yep, times 6. Oh, look at that. Is this times 6? 4 times 6 is 24, over 3 is 8. Yeah, this is times 6. So what do we got here? We know this is a geometric series. Okay, so how do we get this geometric series? Well, let's see what we got. We got 4 thirds, and we got to multiply that by 6, right? A repeated number of 6s. So how are we going to get that? Let's see. This one needs to be 4 thirds times 6. We don't want 6 for the first case, so we want this to be, let me redo this actually. For the first case, this is going to be 4 thirds times 6 to the power of 0. This is 4 thirds times, then we need 6, right? That'll give us 24 over 3 is 8. Over here, we're going to get 4/3, and then we're going to need 2 6s there, so 6 squared, 36. There we go. And then this is going to be 4/3 times 6 to the third then, right? We multiplied it by 3 times by 6. Okay, so what do we got here? We got 4/3, that's something in common among all of them, times 6 to the power of 1 needs to give us 0. 2 needs to give us 1. 3 needs to give us 2. So we need to take it to the power of n minus 1. Always 1 less. There we go. Okay. All right. Let's just do a couple more. Hey, we did this one already, didn't we? 0, 2, 5, 9, 14. 0, 2, 5. Oh, look at that. That's number 6 on the previous page. All right. Skip. Let's go on. Number 14. Let's just do one more, and then I will leave the rest for us to do in our Zoom session this week, okay? So let's do number 14. Oops, what am I doing? 1, 2, 3, 4 terms. And we got the values of 5 over 8, 9 over 16, 13 over 32, and 17 over 64. All right, I'm going to take this a piece at a time. I hope you see the pattern that I see here. What I'm noticing is, first of all, 8 times 2 gives 16. 16 times 2 gives 32. 32 times 2 gives 64, right? So the bottom is basically multiplying by 2 every time. Repeated multiplication of 2, okay? So what is this? Well, 8 is the same as 2 to the third then. And then we always need to have one more 2 after that. This is 2 to the fourth. This is 2 to the fifth. This is 2 to the sixth. All right, well, what's happening on top? Let's see. 5 to 9. We'd have to add 4 to that, right? 9 to 13. Add 4. 13 plus 4 gives us 17. So it looks like the top is actually turning into an arithmetic sequence on its own. It's arithmetic sequence where the 4 is the common difference, so 4n, and then you want that value, let's say it's plugging in term 1. 4 times 1 gives us 4. How do we get 5? Plus 1. Let's see if it works. 4 times 2 is 8. Plus 1 gives us 9. 4 times 3 is 12. Plus 1, 13. 4 times 4 is 16. Plus 1. Yeah, this is working. Awesome. So the top is going to basically be to the 4n plus 1 then. That's going to be all the top. All right, let's put this all together. On the top, what we've got is 4n plus 1. What do we have on the bottom? It's 2 to the power of stuff. 3. 1 needs to be 3. 2 needs to be 4. Term 3 needs to be 5. What are we doing with each of those term numbers? Hopefully you're saying you're always taking that and adding 2 to it. So we have 4n plus 1 all over 2 to the power of n plus 2. n plus 2 is its power there. There we go. Okay, so that'll be our formula for number 14. And that will conclude our video for today. We will finish everything else on Zoom Day. See you then. Stop.